Hello, everyone. My name is Ben Bruce. I'm a graduate student at UW-Madison, and this is my video contribution to the Fourier Restriction Online 2021 workshop. And first, I'd like to thank the organizers of this nice workshop for giving me the opportunity to participate. So as you can see, my topic for this talk is restriction to hyperboloids. And this is based on a few projects I've worked on over the past year or so, one of which was joint with Diogo Oliveira Silva and my advisor, Betsy Stovall. So the outline for my talk is the following. I'll start with a bit of background just on the restriction conjecture, and given the focus of this workshop, this will be fairly short. And then I'll go on to the main topic of the talk, which is restriction to the one-sheeted hyperboloid in R3. And so here I'll be focusing mainly on global estimates, meaning estimates that are valid on the entire surface rather than just on a fixed compact subset of the surface. But then I'll talk about the state of the local estimates for this surface in R3, and I'll discuss how improvements to the local estimates can give improvements to the global estimates. And then finally, I'll talk about restriction to higher dimensional hyperboloids, where it's most natural to first study two-sheeted hyperboloids. Okay, so the restriction conjecture. The purpose of this slide is mainly just to explain the notation I'll be using. So S will always denote a smooth hypersurface in Rn, a hyperboloid in this top. And d sigma will be a measure on S. Usually it will be the Lorentz-invariant measure on the hyperboloid, and I'll say a bit more about that later. But for now, S and d sigma are just an arbitrary smooth surface and a measure. Once we have these, we can define the extension operator E in the usual way. And then now we can state the restriction conjecture in kind of a general form. It says if S is compact and has k non-vanishing principal curvatures, then the extension operator is bounded from LP to LQ when P and Q lie in a range that depends on the number of non-vanishing curvatures. So an important remark to make is that the case where S is not compact is also interesting. And in many natural situations, scaling relations exhibited by the surface can replace the compactness assumption. And there has to be an additional condition imposed on the Lebesgue exponents. So for example, if you think about the paraboloid or the cone, these exhibit nice scaling relations. And if we impose a scaling condition on P and Q, in fact, by taking equality here in this condition, then you can just rescale the local estimates, say near the origin, to obtain global estimates. The hyperboloid, however, does not exhibit it doesn't exhibit a scaling relation in this sense, but geometrically it sits between a paraboloid and a cone. And so still the geometry is pretty nice, and we can kind of combine methods associated with the restriction theory for these surfaces to get the global estimates that we're aiming for. Okay, so let's take a look at the one-sheeted hyperboloid in R3. You may not have thought about this surface for a while. So here's what it looks like. Near the origin, it has good curvature. It looks like it's a hyperbolic surface, so it looks like a hyperbolic paraboloid, in fact, near the origin. But then as you move away from the origin, it's asymptotically conic, so it flattens out. But nevertheless, it always has strictly non-zero curvature. And then another couple of important properties that I won't get into the details on these and like where they come up so much, but they are important for the proofs, namely that the surface is doubly ruled and it's invariant under Lorentz transformations. Okay, so this is what we need to know about this surface. So let's turn to the main topic, which is global estimates for the one-sheeted hyperboloid. So I'll denote the surface by S, and this is how you might express it in coordinates. And as I suggested at the beginning of the talk, it's natural and really necessary to equip S with its Lorentz-invariant measure, rather than, say, the standard induced Lebesgue measure. So the reason it's natural is probably obvious. We want to be able to freely apply the Lorentz transformations, the symmetries of this surface. But another reason why we want to choose this measure is that it coincides with the so-called affine surface measure on S. And this means that d sigma places less weight on regions of the surface that have less curvature. And this is nice because since our surface is asymptotically conic, its curvature is sort of degenerate, right? And so normally degeneracy and curvature would destroy your hopes of proving like a non-trivial range of restriction estimates, but because our measure penalizes the regions of this surface that have little curvature, we can obtain a more robust range of extension estimates. Okay, so given the surface S and this measure, E is the corresponding extension operator, and we'll also need some notation for the parabolic region near the origin. So just sort of truncating the surface near the origin. So that I'll call S0. Okay. So the main result that Diogo, Betsy, and I obtained has two parts. The first just gives a range of LP to LQ boundedness for the extension operator. So global estimates for this surface. So let me try to put these conditions in context here. So firstly, we see the range Q greater than 10/3. 10/3 is the endpoint of the bilinear restriction range in R3. So that's where that will come from. And then there are three conditions imposed on the exponent P. So the lower endpoint here, Q over 2 prime, P equals Q over 2 prime corresponds to the green line in this picture. And this green line is the conjectured range of the conjectured range of boundedness for the extension operator for the paraboloid and the hyperbolic paraboloid in R3. This upper endpoint, P equals Q over 3 prime, corresponds to the red line in this picture, which is the range of boundedness of the extension operator for the cone in R3. And then the condition that Q is greater than or equal to P basically just comes from the fact that we're working on an unbounded surface. Okay. So in short, what this statement shows is that at least in the range where Q is greater than 10/3, so beneath the dotted line, the extension operator for the hyperboloid kind of interpolates the range of boundedness associated to the cone and the paraboloid. Okay, so here's the second part of the theorem. And the numbers here are a little bit hard to parse probably, but what this is saying is conditional in nature. It says if we have an estimate on the compact region S0 near the origin, and remember S0 looks like a hyperbolic paraboloid, then we get then we get a corresponding range of global estimates. And in particular, if we have an estimate like this where Q0 is less than 10/3, so an estimate for exponents belonging to the green line, but in the little portion above the dotted horizontal line. So if we have an estimate on S0 for exponents that lie on this top portion of the green line, then we get an improved range. We also get an improved range of global estimates. Okay, so let me try to say something about the proofs of these results. So I'll start with part one. So we want to prove global extension estimates on this surface. So the first thing we're going to do is divide the surface into dyadic annuli. We already have defined S0 to be this region near the origin, but away from the origin, we divide the surface into annuli Sn. And then on each annulus, we want to prove extension estimates that are uniform in the parameter n. And this is really the core of the proof of this result. Okay, so if we have these uniform estimates, then the next thing we want to do is sum over n. But when we sum, we will get some diagonal terms and some off-diagonal terms. And for the off-diagonal terms, these will be basically bilinear contributions from distinct annuli. So we need to control the bilinear interactions between different SNs. And for this, we use a Strickhart's inequality for the Klein-Gordon equation, and you can pretty efficiently get bilinear estimates that do what we need them to do. And then from there, we can sum using pretty elementary arguments. Okay, so what I want to say a few more words about would just be step 2 in this process. Okay, so we're trying to prove uniform extension estimates on annuli. So how do we get these? Well, in the theorem statement, we saw the range Q greater than 10/3. And this suggests that we'll be using the bilinear method. And we're working on 2 different types of annuli. We have the blue annulus S0, which resembles the hyperbolic paraboloid, and then we had the other annuli colored in red, which were sort of better approximated by the cone. So, so for the conic type annuli, to apply the bilinear method, we'll just try to adapt the L2 based bilinear theory for the cone. And there are various, so this is kind of the proposition that you would expect to be true based on the case of the cone. And there are various ways to arrive at something like this. One could apply the original arguments from the early 2000s, or use more recent results, such as a result of Timothy Candy. And this is what we obtain. We basically take the annulus Sn and we decompose it into sectors of smaller angular width. And then between 2 such sectors with separation, we prove a bilinear estimate of this form. Okay. But we also have the annulus S0, which resembles the hyperbolic paraboloid. So for this, we try to adapt the existing bilinear theory for the hyperbolic paraboloid. And so in this case, we don't decompose into sectors, rather we decompose into sort of rectangular or rectangular-like caps. And these now exhibit a 2-parameter separation condition. So there are two directions of separation kind of parallel to the lengths and the widths of these rectangles. And this is just a rough picture of what it looks like. So between any 2 of these appropriately separated caps, we have this estimate. the proof of this is just based on applying Lorentz and parabolic scalings to kind of convert the estimate into a form where we can apply an existing result of Saint-Nicolas. Okay. Right, but these are just bilinear estimates. We need, what we're trying to prove are linear extension estimates. So for that, we adapt two different bilinear to linear arguments, one of Tau, Vargas, and Vega, and the other due to Betsy Stovall. And the latter one is needed due to sort of complications caused by the two-parameter separation that I described on the previous slide. This causes a slight complication that means that you can't just apply the Tau-Vargas-Vega bilinear to linear argument directly. But Betsy has this result on the hyperbolic paraboloid that can be adapted to this situation. Okay, so that was part one, the unconditional bounds. Let's take a look at the proof of part two, and I'll remind you what that said. So it said that if we had an improved extension estimate on S0, meaning an extension estimate for exponents belonging to the green line, but above the dotted horizontal line here, then we also get a range of global estimates above the dotted line. So in other words, improved boundedness on the parabolic region implies improved boundedness globally. That's what we're trying to show. So the basic idea for showing this is the following. We conditionally, or by hypothesis, we have an improved range of estimates on S0. So what we will do is show that this implies an improved range of bilinear estimates on each annulus Sn. And then by running the same sorts of machinery I was just describing, namely bilinear to linear arguments and like summation techniques, we ultimately get new global estimates on S. Right, so it's really only the first implication that's interesting, I guess. And the key ingredient here is actually conic decoupling. We basically, there's a point at which we directly use the result of Bourgain-Demeter. So let me just try to describe where decoupling enters this argument. And I'll just do this through a picture. So we are trying to, so conditional on improved estimates on the 0 scale portion of the surface, we're trying to prove new bilinear estimates on these annuli that lie far from the origin. Okay, so here I've drawn one of these annuli, Sn. So the bilinear theorem that we're trying to prove takes place on sectors of smaller angular width. So we take a pair of sectors that exhibit some separation, and we try to prove a bilinear estimate between these. So what conic decoupling allows us to do is, instead of proving an extension estimate from one of these wider sectors in red, we can instead decouple that estimate into contributions from much thinner sectors, which I've colored in blue. And basically, we can just deduce this directly from conic decoupling because the cone approximates the hyperboloid, and the approximation gets better the further you move from the origin. Okay, so then this leaves us to study extension estimates on these thinnest blue sectors. But at this really thin scale, the geometry of the surface actually becomes more favorable than that of the cone. At this scale, we can see the the additional bit of curvature that the hyperboloid exhibits compared to the cone. And more precisely, to harness that, we can just, if we're working on a sector of this size, so a very thin sector, then we can apply a Lorentz transformation to map it into S0. Okay, so then we have better estimates on S0, so we apply those. That gives us better estimates on the thin sector, and then thin sectors, and then by conic decoupling, we get better estimates on the wider sectors. Okay, so that concludes the discussion of global estimates for the one-sheeted hyperboloid. But there's a natural question, which is we have this conditional result that says if we have better local estimates near the origin, then we get better global estimates. The natural question is, what's the state of the local estimates for this surface? Right, so as a parallel project, I was working on proving a local estimate that could be sort of directly plugged into the conditional result I was just discussing. And this is the local estimate. So S0 is, as before, the parabolic region. And the estimate is that if Q is greater than 3.25 and 2p prime is less than Q, then we have boundedness from LP to LQ. Okay, and technically to technically to apply this to the conditional result, part 2 of theorem 1, this estimate needs to hold on the green scaling line, so in the endpoint case. But this theorem does actually also hold in the endpoint case to show that one additional ingredient was needed, which was obtained separately with Diogo and Betsy. So the proof of theorem 2 I won't get into, but as you would guess from the 3.25 here, the proof is by polynomial partitioning. And in the case of the hyperboloid compared to the paraboloid and the hyperbolic paraboloid, Lorentz symmetries play a key role. And these especially are important in determining the appropriate transversality conditions for bilinear type estimates. Okay, but the upshot of this is that now we have a local estimate that goes beyond the bilinear range. So Q here can be less than 10/3. And if you now plug that into the conditional portion of theorem 1, then we get the following global estimate in the range Q greater than 102/31. And this is just modestly better than the bilinear range. Okay, so in the last couple minutes, I just want to say a few words about higher dimensional hyperboloids. So as I said at the beginning, when you go to the higher dimensional setting, it's actually easier to work with two-sheeted hyperboloids instead of the one-sheeted hyperboloid. And so I'll say more about that in a minute, but indeed theorem 1 does generalize in a pretty straightforward way to the case of two-sheeted hyperboloids in arbitrary dimension. Okay, but why are one-sheeted hyperboloids apparently harder? It's because they're hyperbolic. They have curvatures of negative. They have curvatures with different signs. And while there's been a lot of activity and progress on restriction to hyperbolic surfaces in R3, relatively less is known about hyperbolic surfaces in higher dimensions. So one exception is the higher dimensional hyperbolic paraboloid or paraboloids, where Alex Barron has made some recent progress, but on the whole, less is known about hyperbolic surfaces in higher dimensions. Okay, but right, so let me just sort of flash the theorem for the two-sheeted case. It's a lot to process, but I'll just simply say that this is the natural higher dimensional analog of theorem 1, which I displayed before. So in particular, part 1 here gives a range of unconditional global estimates on the two-sheeted hyperboloid in Rn. And then part 2 gives a conditional result, which again takes conditional improvements near the origin, and converts them into improvements to the range of global estimates. However, now, since the two-sheeted hyperboloid is elliptic, S0, meaning S0 is a compact elliptic surface, this may lead to some possible improvements to the result. Namely, while this local estimate that I proved for the one-sheeted hyperboloid was new, there are already sort of a wealth of recent estimates for elliptic surfaces, compact elliptic surfaces. And so one could take these state-of-the-art results and just plug them into the conditional result from the previous slide and see what that gives you. And it does lead to an improvement in like sufficiently high dimensions anyway. There's kind of some arithmetic that you need to do in some bookkeeping, because you need to make sure that the estimate you're applying is scale invariant. But this can be dealt with. Okay, and then slicing leads to a second type of conditional result on the conic line. And this allows you, again, to use the existing elliptic estimates, but this time applied to spheres one dimension lower, which make up the cross sections of the hyperboloid. And right, I think that's all I wanted to say. So thank you very much for your attention.